So picking up where we left off last time, we were finishing up at least the first 30 elements in the periodic table doing their electron configurations. And we're going to find, as we end chapter 7 and go into chapter 8, that the electron configurations are very important for the properties of the different elements. And so if you look at the valence shell electron configuration of elements in the same group, we'll notice that the number of valence electrons for elements in the same group is going to be the same. So the core electrons may differ, but the number of valence electrons will be the same. And that's what largely leads to the properties of the different elements. And that's why it was so important to be able to fill out all of these electron configurations of the different elements. So we went through the first 30 elements, but you should be able to go through and at least come up with basic electron configurations for all the elements in the periodic table, assuming you know the ordering of the energy levels of the different orbitals based on what we did a couple days ago. Okay. And so hopefully you've had a chance to fill out the electron configurations of all those 30 elements and check it with what we have on here. Remember, there are a couple of exceptions when you get to chromium and copper, which are noted by the stars on the left of this page. So in those ones, the 4s shell is half filled, whereas the 3d is either entirely half filled or fully half filled, as opposed to pairing up the electrons in the 4s orbital first. And so that these things are going to be important for not just the electron configurations and bonding, but for understanding ions of transition metals as well, which is something you'll actually explore more in 102 if you go on to 102. So the last section of chapter 7, 7.12, is periodic trends and atomic properties. And remember, when we think about the periodic table, the reason it's called the periodic table is periodically, if you're going from elements 1 through 118, periodically you encounter an element that has similar properties to another element or another couple of elements. And so when we think about periodic properties or periodic trends in the properties, these trends are going to show how the different elements are related to each other. And largely, we're going to consider these trends to be either a trend within a group or a trend within a period, and then we can combine those to give us a periodic table trend. So the first two periodic trends that we're going to look at, as you can see, are the first ionization energy and the electron affinity. So the first ionization energy is really just the amount of energy required to remove the first electron, to essentially create a +1 cation. Okay, so that's really what we're talking about. It takes energy to do this, right? We're pulling an electron away from the nucleus and core, essentially. So you have this negatively charged electron, the positive charge of the rest of the atom, and it takes energy to pull those apart because the electron is attracted to the positively charged rest of the atom. And so the trend in the periodic table is such that if you start, and we'll just compare a couple of different groups, in particular the noble gases, right? So you can see there's a decrease in the amount of energy it takes, right, to remove an electron from a noble gas as you go down the periodic table, right? So there's an overall decrease there. The other group we'll look at is the alkali metals. Okay, you'll notice I'm circling those. Again, there's a decrease in the amount of energy it takes to remove that first electron, okay? And so that is a decrease from top to bottom within a group. Okay, remember within any given group, there's a decrease in the amount of energy it takes from top to bottom, meaning that as you go down the periodic table, it takes less energy to pull away the electrons. And the reason for that really just has to do with the size of the atom. Remember, you're going to basically be taking an electron from this outer shell, this valence shell. And when you take this electron from the valence shell, it's farther away from the nucleus, which is where all the positive charge is. And based on what our experience should be, hopefully you've had a chance to play with magnets sometime in your life, right? When the magnets are closer together, they pull on each other more. When they're farther apart, they pull on each other less. So if you have two magnets that are already far apart, it's going to take less energy to pull them apart all the way. Same idea here, only we're talking about the charges of the electrons versus the nucleus. If you have an electron that's farther out, right, which would occur when you have an electron in a valence shell that has a higher principal quantum number, it's going to be easier to pull that electron away. And that's why there's a decrease from top to bottom for the amount of energy it takes to remove an electron. The other part of this trend that we'll look at is the trend within a period. And so we're just going to look at the second period. In particular, if you go from lithium all the way up to neon, you'll know that there's an increase. Overall, there's an increase in the amount of energy that it takes going from left to right, okay? And so on this one, there's an overall increase in left to right, and there's some other subtleties to this, but what you find is the increase going from left to right occurs again largely because of the distance from the nucleus that these electrons are. Now we're going to see something about the size within a period in just a minute, and that'll be in the atomic size trend, which is going to come after we talk about electron affinity. But there's a subtlety to the size of the atoms as you go from left to right across the periodic table. And there's another property that we're going to start to explore at the beginning of chapter 8 called electronegativity, which really talks about how much these atoms pull on the electrons overall. And so that's going to, those two things, the size of the atoms and the electronegativity, right, properties that we're going to look at later, are going to be what determine why the first ionization energy increases going from left to right across the periodic table. But you'll notice that if you look, so you've got lithium is your first one, right? There's lithium there. Then you have beryllium. Okay, there's beryllium. And then you have boron, third, carbon, nitrogen. And so once you go from, the electron configuration of the valence electrons, where lithium is 1s or 2s2, beryllium is, sorry, lithium is 2s1, beryllium is 2s2. That's a full orbital. And then when you go to the next electron configuration for boron, now you have 2s2, 2p1, and it takes a little bit less energy to remove the first p electron, if you will, than it does to remove the second of the s electrons. And so there's some subtleties here. You'll notice that there's little jagged steps where you have either a fully filled shell, so it takes more energy to pull an electron from a fully filled energy level, or orbital, or you have a fully half-filled shell. So here is boron, then carbon, then nitrogen, and nitrogen has a half-filled set of p orbitals. All of the p orbitals there have one electron in them. When you get to oxygen, now you have all of them, you have half-filled orbitals, but you also have one filled p orbital, and that's a little easier to pull out that first extra electron, if you will, beyond the half-filled shells. And so you get that kind of a trend in the ionization energy. Little subtleties across the period, but overall the trend is increasing from left to right across the periodic table. Okay, so that's the first ionization energy. Again, the amount of energy it takes to remove an electron. The next trend is called electron affinity. Okay, and in general, you can think about electron affinity as the energy released when an electron is gained. And so on this one, we can again look at the basic trend. It's just especially important when you start to look at, say, the noble gases, and anything from period 3 and below, this trend becomes really good. But you'll see that if you look at chlorine, fluorine, chlorine, bromine, iodine, and astatine, those are the halogens. If you look at those, you'll see that when chlorine gains an electron, it releases quite a bit of energy, and bromine releases just a little bit less, and iodine just a little bit less. And again, this is going to have a lot to do with the atomic size and the electronegativities. But basically, chlorine really wants to gain an electron, so it's going to release a lot of energy, go to a more stable state. Bromine is going to also want to gain an electron. It's going to go to a more stable state, but it's going to release a little bit less energy than the chlorine does as it becomes chloride. And so that's the trend is basically for electron affinity. There's a decreasing electron affinity going from top to bottom again. Okay. Yes, Amir.
Why fluorine is different? That's the first one on that group.
Yeah, so you'll notice that, in fact, the first 2 periods tend to sort of be off a little bit. And that's really because the electron shell, I mean, it's basically so small at that point. There's some other factors that go into that. And so it doesn't fully follow the trend for the first 2 periods of the periodic table. It has, like, fluorine is, for example, the most electronegative element, and it's very small. Again, electronegativity, a trend we're going to look at later, and atomic size, a trend we're going to look at a little bit later. And those 2 things have a lot to do with how the atom will gain or lose energy as it gains or loses an electron. All right, so the main trend to look at is really decreasing electron affinity from left to right. So it follows the same trend as ionization energy.
Left to right or top to bottom?
Oh, sorry, this is from top to bottom. Thank you. From top to bottom. But if you go from left to right, it's actually increasing, right? So it increases from left to right. It follows the same trend as ionization energy. And so more on that after I actually write it. Okay, so when it comes to the electron affinity increasing from left to right, again, and you can see that through, if you just look at overall. Now, again, this is not the greatest one to look at, but if you look at that 3rd period especially, right, overall there's this trend of increasing. And again, it follows that sort of that jagged increase that ionization energy does. But basically, it's again because of these properties of atomic size and electronegativity. Essentially, how much do the atoms want the electrons? And that's related to certain things about the pull of those electrons and the size of the atoms. And so the overall trend shows an increase from left to right, or if you want to say, and a decrease from top to bottom, or you could say an increase from bottom to top. And we'll look at this a little bit more as we put all of these trends together in a minute, okay? The whole idea is it's a whole heck of a lot harder to pull an electron away from something that's way up in the top right-hand corner. And if it's harder to pull the electrons away from something that's up in the top right-hand corner of the periodic table, it's probably going to be easier for one of those elements to grab onto an electron. So that's sort of the trend is the same for these, if you think about it from the standpoint of whether an element is taking or losing electrons. It's basically the same type of a trend. The next one that we're going to look at.
The question. So is hydrogen the hardest because it's number 1 to pull away?
No. Hydrogen, so because if you look at it, right, hydrogen is going to have, if you look at the decreasing electron affinity and the decreasing ionization energy from top to bottom, in hydrogen's group, it will have the highest ionization energy, right? So if you compare hydrogen, which is, so let me go back to, let me change my color here so you can really see it. If I go back to the ionization energy chart and I consider that first group, right, here's hydrogen way over here, right, and hydrogen's above lithium, right, sodium, potassium, right, so there's a decrease from top to bottom, and actually hydrogen's pretty pronounced. It takes considerably, well, it takes more energy to remove the electron from hydrogen than it does from lithium, sodium, potassium, in that order, right? And so if you look at it as far as electron affinity, it's going to be easier for hydrogen to grab onto an electron than it is for, say, I'm circling the hydrogen there on the electron affinity one, than it is for lithium or sodium, right, or potassium to grab onto one of those extra electrons. So so that's one that you want to compare within that group, right? If you look at hydrogen, say, compared to helium, hydrogen will have a lower ionization energy than helium, right? It's, in other words, it'll more readily give off its electron, but it'll also more readily accept an electron. You'll notice, especially if you look at the noble gases and the electron affinity, right? Those have very, very low electron affinities, right? Noble gases have this inherent stability. Oop, I totally circled zinc there. There's an inherent stability to the noble gases electron configurations that we kind of saw when we were filling the periodic table with their electron configurations. And seeing that, oh yeah, well, before we start to fill the next shell, you know, we have this core set of electrons, right? And then the next shell you go out to is much larger, so it's not holding on to the electrons as strongly. So the noble gases are a little different too.
I guess I'm just looking at the periodic table. They were saying lithium would grab on. You said would decrease because you're saying because decrease from left to right, but lithium is all the way on the left.
No, increasing from left to right and decreasing from top to bottom.
Okay. All right. Thank you.
Yeah. Mm-hmm. Okay. So if we look at the periodic table, and in particular, the trend that we want to look at is in atomic radii. Atomic radii is essentially, and so we're calling it atomic radii. You can think about it as atomic size or size of the atom. And what we're going to be interested in here is really two parts, really the main group. So the part here that I'm circling on the right, which is the p block, right, where the last electrons you put into the electron configuration fall in the p orbitals, and then the s block. We're not going to worry about the electron or the atomic sizes of the transition metals or the lanthanides and actinides here. We're going to stick with just the main group. And if you look at the main group, the atomic radius is going to increase, going from, as you can see from the arrows, there's an increase from right to left on the periodic table, right? So there's an increase from right to left, and there's an increase going down, okay? So we're gonna explore the increase going down first. And so we can look at the increase going down. Let's just look at hydrogen, the first group, the alkali metals and hydrogen. So as you go down the periodic table, the reason that the atomic size gets larger, remember the atomic size here, the radius, is the distance of that you go from the nucleus that incorporates, you know, 95%, 99% of the electron density of that atom. So as you go from hydrogen, which has just its 1s electron, to lithium, now on lithium you have a 2s electron, but you have the core of the 1s, so that 2s electron is farther out, right? So each time you go down the periodic table, down to sodium, now it's a 3s electron. Potassium is a 4s. So each time you go down from one element to another down a group, you're going to where the valence electrons are farther and farther away from the nucleus, and so that atom is going to be a bigger atom. Okay, so more shells means that the atom is going to be bigger. And that's a pretty straightforward reason for the atomic size to increase, right? You have more electrons and they're in larger shells, it's going to increase. But if you look at the other trend, the other part of this trend, where as we go across a period, right? So it was written here as increasing atomic radius from from the right to left, right? So my arrow was right to left increasing. Okay, that is, I think, harder one to visualize, and I'll try to explain this even better here, right? Than just giving you the direction. So we say, okay, the atomic radius is increasing from right to left. It might actually help us to think about this in the other direction. So let's look at the second period. Okay, so the second period here, if we look at boron, carbon, nitrogen, oxygen, fluorine in particular, right, you can look at there, if it's increasing from right to left, it would be decreasing from left to right. And the way to think about this is as you go from boron, right, to carbon, to nitrogen, at each step, you're adding another proton to the nucleus. As you add another proton to the nucleus, it pulls those core electrons in a little bit tighter, right? So you go to boron, from boron to carbon, those core electrons are pulled in a little bit tighter, which means the valence electrons can be pulled in a little bit tighter. So each time you add a proton, core electrons are pulled in tighter, pulled in tighter, pulled in tighter. You go to from boron to carbon, to nitrogen, to oxygen, to fluorine. You keep pulling those electrons on the inside in tightly. You get to neon and you've pulled them in as far as you can pull them, and there's no space to put in any more electrons. And that's why when you go from neon to sodium, as the atomic number goes up, well, there's no more place to put electrons, even though you're putting another proton in the nucleus, so that next electron has to go into the next shell, which is farther away. So you have these subtle decrease, from right to left as you go across the periodic table until you fully fill a shell. And then when you fill the shell, there's a big increase as the next electron goes in after that shell is filled. So as you go across the periodic table, it decreases, decreases, decreases. You get to neon, right? You get to that noble gas. There's no more space to put any more electrons, so the next electron has to go out farther, and there's a big increase. So as you go across the periodic table from left to right, there's small decreases, but when you go down a group, there's big increases, and this all has to do with those electron configurations and where the electrons can fit around a nucleus, okay? And so what's causing that, the core electrons to be pulled in, thus the valence electrons to be pulled in tighter as you go from right to left. What's causing those to be pulled in is just the fact that the nucleus has a higher nuclear charge. And it'll pull it in until, again, there's no space for more electrons. So that's the trend in atomic radii, okay? And so if we put these together, the ones that we've looked at so far, right, are ionization energy, right? So ionization energy increases from left to right and increases from bottom to top. Okay, we've also looked at electron affinity, where electron affinity increases going from bottom to top, increases going from left to right. And we've also looked at the other one is atomic radius, where we have an increase in atomic radius going from top to bottom and an increase in atomic radius going from right to left, okay? Another thing we've explored already, and we've talked about a little bit, is the metallic character versus the non-metallic character, right? And this is something we talked about based on just identifying elements in the periodic table and where they are, right? Remember our non-metals were all up in the top, right corner. And then the metals were the rest of the periodic table. And so you can consider there to be a spectrum of metallic character and non-metallic character, where the more metallic things are going to be farther to the bottom and to the left, and the less metallic elements are going to be farther to the top and to the right, okay? So that's another trend we kind of talked about before, because we just know where to identify those metals versus non-metals in the periodic table. And when we think about metallic character, remember this is things like they're shiny, they're conductive, right? So metals will be more shiny, more conductive, more ductile, that kind of thing, whereas non-metals will be less so. Okay. So there's one other trend here that we haven't talked about, and we're going to jump into that early in chapter 8, and that is the electronegativity. So electronegativity is something we're going to come back to very soon as we proceed through and into chapter 8. Okay. So right now I'm actually going to stop recording here for a second and get chapter 8 up and ready to go.